Welcome to the third video on stress combinations. In this one, we continue the second example we've been doing, determining the actual stresses experienced at points D and E on the cross section. Let's consider point D first. So we want to use those four equations that we talked about earlier to deal with the axial load, the bending stresses, the shear stresses due to transverse loading, and the shear stresses due to torsion. So let's do the axial stresses first. So that's going to give us pure A, 0. Cool, very easy in this case. Now let's do bending. That's going to be moment times distance from the neutral axis divided by the second moment of inertia, which in this case is going to be 50 kip inches times 0.75 inches divided by second moment, which, what did I say that was? 2.48. That's going to give us 15.1 KSI, and that's tension, right? Tension KSI up here at point D. Now let's look at the stresses. So from the transverse loading, we're going to be looking for, I just drew the same character twice. Q times V over the second moment of inertia and the thickness. Well, that's easy though. That's going to be 0, because at the very top, Q is going to be 0. Now, some of you might also be going like, oh, but Dr. Butters, T is also 0. And that's true. That's true. That's a good point. You're going to have to look at, I guess you could look at the limits of this as T approaches 0 and Q approaches 0. You're going to find the Q gets to 0 a lot quicker. Just to say consistent with everything. Also, our boundary conditions say that it has to be 0 at D. So we don't have any stress due to the transverse loading. We will have shear stress due to torsion, however. So due to torsion, and that's going to be the torque times our radius and divided by our J. J. So that's going to be, in this case, because we're all the way at the top, this is going to be 0.75, so we're going to have 20 kip inches times 0.75 inches divided by 2.48 inches to the fourth, and that'll give us 6.04 KSI. Now, when we're looking at the torsion stresses at point D, do note that because this is torsion and we're looking to induce moment about the z-axis, which is to say about about the center of this, there's a little twist, that means that the shear stress here is not going to be in the y direction, right? It's not going to be up and down at point D. It's going to be to the side to side, because that's going to be how we're going to induce moment. Okay? Keep that in mind, that the torsion distribution, it's going to be, you know, it's going to be down over here. It's going to be up over here, depending on which portion you're looking at. So, depending on, you know, if you cut right here and you're looking at this half, then yeah, that's what it's going to be. If you're looking at this half, obviously it will be the other way. But all of the shear stress values will be the negative of that. So that's important to remember, that this is actually like shear in the YZ direction, I guess. So, or the XZ direction. XZ direction, yes. So now let's look at, because this was for point D. Let's consider a different point. Let's consider point E. That's the one that comes after D. And at point D, we can, or at point E, we can gratifyingly, you know, say that the axial stress is still 0. The bending stress is going to be different, though, and that's going to be we're going to have the same moment, we're going to have the same second moment inertia, but instead of having 0.75 for our distance, we've got 0. So very cool. At point E, in this case, we don't have any axial loads. What's our shear stress? Our shear stress here, due to transverse, is going to be equal to Q times V I times T. We've got that, we've got that, we've got that. For this, right, so Q, remember, is A times Y, which is going to just be 1/2 pi times, let's put parentheses there, R squared times Y on the centroid of a half circle is going to be at 4/3 times R divided by pi. How convenient that those pi's cross out, and we're going to end up with 2/3 times 0.75 cubed. So that's going to end up being 0.28125 cubic inches. We're going to end up with this transverse stress being 5 kips times 0.28125 inches cubed divided by 2.48 inches to the fourth, and also the thickness, which at this point is going to be 0.75 inches, and that's going to give us, well, just 0.755 KSI. And finally, our torsion will be the same in magnitude, but not in direction, because remember, this was in this direction, whereas this is going to be in this direction. So, torsion is going to be equal to negative 6.04 KSI. So what that means is that when we're at point D, the transverse shear is going to induce a shear that is what we would normally consider to be a positive direction of shear, but the torsion is inducing a shear stress that is what we would normally consider to be a negative direction for shear. And that means that overall, right here we didn't have to really do this because we had one normal stress and one shear stress. But we're going to have our bending stress at 0, and our shear stress is going to be the sum of these two. So it will be negative 5.285 KSI. However, if we had considered point F, the transverse shear would be in the same direction. It would be in the positive direction. And the torsion would, instead of inducing a negative direction shear stress, would induce a positive shear stress. So point F, if we look at this whole cross-section, is going to be the point that experiences the maximum shear stress. But points, and if we had some axial load apply here as well, points D or G might be possessive of the maximum normal stress, and it might be somewhere else entirely if we had a load in the x direction, causing moment about the z-axis as well. So we gotta add all these things together to get our total stresses. Now, in this case, we've got zero normal stress at part E. So if we want to determine the principal stresses, that's pretty easy. We just divide our sum of shear stresses by 2, and that's going to be our normal stresses for our principal stresses. For this one, for point D, because we have both shear stress and normal stress present, we're going to have to use some more circle stuff to determine our principal stresses. And it might be the case that we have some extremely high principal stresses here, thanks to our torsion.